Hello everyone and welcome to this machine learning playlist. Today we are covering an important topic, so whether you're someone who is absolute beginner or you have some experience with machine learning, this playlist has been designed in such a way that it will be easy to follow for everyone. Also packed with lots of values and information, and it will be really helpful for you, especially if you're preparing for a machine learning based job role like data analyst or data scientist. So please subscribe to the channel and drop a like below to support our work. And without any further delay, let's get started with today's topic.
Hello everyone and welcome back to this new lecture on support vector machines. This one is going to be the third machine learning algorithm that we are covering within this machine learning playlist. So in case you're someone who is absolutely new to the machine learning field, then I would suggest that please consider watching this playlist from the top, the way we are uploading the videos. And if you have been already following along with us, then without any further delay, let's move ahead. So support vector machines being one of the strongest machine learning algorithms and performs really well in terms of classifying between multiple classes. So let's go ahead and see that how the algorithm actually works and what are the pros and cons of using this technique. So over here on the one-dimensional plane, you can see we have two different classes, and let's try to understand that how the SVM algorithm actually works in order to classify between these 2 points. So first thing that it does is it will draw this classification boundary in order to segregate between these 2 classes, and this line will be drawn in such a way that we get the maximum margin on both the sides. And soon we will understand that why this margin is needed. But as a whole, the idea is to draw this boundary in such a way that we get maximum spaces for these margins. And only after this point, SVM will help you to understand if the final outcome is coming from this class or from the other class. So as a whole, it looks good because it is pretty much understandable that the SVM algorithm is managing a safe distance between these 2 classes, and because of this entire margin, we will feel confident around the prediction. We will feel confident with the output of the SVM algorithm. But let's imagine a different situation here. Let's say that you have one outlier from this class at, let's say, this point over here. In that case, if we go by the basic approach of the SVM algorithm, it will draw the boundary over here, and the margin will be extremely less, something like this. And this will be the total margin that the algorithm will draw for us. And then let's say we have an input that wants to know what will be the class falling at, let's say, this point. Then the algorithm will end up misclassifying that, saying it belongs to this particular class. But visually we can understand that definitely this point belongs to this class. And this is where we come across an issue that needs to be fixed, and we need to get aware of the concept of hard margin and soft margin. Let's try to understand what is that. So let's try to understand the same concept on a 2D plot, this being the x-axis and this being the y-axis, and this will be the classification boundary drawn by the SVM model, and these 2 lines being the margin, the classification margin for the SVM model. It looks pretty good so far, but the problem that we were discussing around that, let's say if we have an outlier over here, okay, in that case the position of this entire boundary along with the margin will shift downwards, and this will decline the performance of our model. In simple words, our model will end up misclassifying a lot of points, and this is where we need to understand the concept of hard margin and soft margin. So when we say soft margin, what we basically mean is that even if we have few data points inside the margin, let's say we have one data point here like this, and let's say if we have a data point over here, and from the other class, let's say if we have a data point here and here, we are going to tolerate that. Okay, so soft margin is one of the parameter for the SVM model, where we explicitly mention that even if we have few data points inside the margin boundary, we are going to allow that, because we are focusing more towards having a generalized model. And it also makes sense visually as well, that even if we are allowing few data points inside the margin, keeping the margin and the decision boundary at the same place, this will still do well in terms of classifying the output for us. But let's say as the model parameter, instead of setting it as the soft margin if you are setting it as hard margin. In that case, it will not allow any data point inside the margin boundary, but that might lead to poor performance of the model sometimes, especially when the data is not linearly separable. Alright, so it was pretty much decent and straightforward to understand that when we have two classes which are linearly separable, then how the SVM model is helping us in order to draw a classification boundary along with the margin, and how can we regularize that margin, keeping it as a soft margin or hard margin. Now let's move ahead and explore further this topic of SVM. We have already seen that when the data is linearly separable, then how the SVM model is actually working in order to do the classification. But now let's have a look on a different and interesting use case. Please consider this example over here, where we have two different classes which are overlapping with each other. Over here, it is not possible to draw a boundary. No matter how hard you try, it will end up misclassifying a lot of data points. Even over here, if you have a look at this observation, again, it is not possible to draw a boundary that can do well in terms of classification. And it is visibly understandable that why is that? This entire data set or the two different classes are not linearly separable. This is why it is not possible to simply draw a straight line in order to do the classification. And this is the exact place where the kernel trick, or you can say the strength of the SVM algorithm, comes into the picture. So before we have a look at different types of kernel tricks, let's try to understand as a whole that what exactly it is doing. In simple words, kernel trick transforms a data from low dimension to higher dimension. What I mean to say is, over here you can see the data is one dimensional. It is plotted on a straight line. And if we are able to choose a correct kernel to transform this data, this will be transformed something like this over here. And now it has been converted or transformed from 1D to two-dimensional data. And now you can see this can be easily separated by drawing a decision boundary with the help of SVM. Otherwise, you would also think that even logistic regression is also able to draw a classification boundary between two classes. Then why exactly we are using SVM? This can be asked in the interview as well. So the main strength of the SVM algorithm is the kernel trick that has the ability to transform the data from low dimension to higher dimension. Again, if you pay attention to the second example over here, we had these classes overlapping with each other, but choosing a correct kernel trick helped us to transform this data in such a way that now it is able to draw a hyperplane in order to classify between these two classes. In case you are not familiar with the term hyperplane, let me give you a super quick explanation. Let's say we are talking in terms of one dimension and we have two different classes. Then the separation boundary could be a simple point in a one-dimensional plane. Let's say we are talking in terms of two dimension and we have data like this. In that case, the classification boundary will become a straight line like this. Of course, along with the margin and all. But let's say when we are talking in terms of higher dimension, we have a three-dimensional data. In that case, of course, we cannot separate these classes only with a straight line. In fact, we will need a hyperplane like this that will do the classification. I understand my drawing is not that good, but you get the idea that when we are moving from two-dimensional to higher dimension, let's say 3-dimension, 4-dimension, or n dimension, which is of course not possible for me to draw on the screen. At that time, in order to draw the classification boundary, the work will be done by a hyperplane, which is nothing but a plane on a higher dimensional data. Now I will quickly erase this. Now let's quickly explore these kernels one by one. So linear kernel is the first one that we explored initially, or you can say, for example, this one, where two different classes can be simply classified by drawing a straight line, of course along with the margin in terms of SVM. But what is a polynomial kernel then? Polynomial kernel is a trick where we need to choose a value of d being the degree of polynomial. And what it simply does is, let's say that you have chosen the value of d as 2. Then for each and every data point within your observation, it will do the square for each and every observation. And then your data will start looking something like this. Let's say it looks like this. And then it will try to draw a straight line in order to classify between these groups. As you can see, this particular one-dimensional data has been transformed into something like this just because we have used a polynomial kernel. And you need to try with different values of d. Let's say you tried with the value 2 and it is still not possible to draw a hyperplane in order to classify between these groups, in that case you can try to change or play around with the value of d, and that value will be applied as the degree of polynomial on each and every data point. For example, if you are choosing the value 3, then the polynomial kernel will transform each and every data point by taking the cube of each and every value. If you choose the value 2, then it will square each and every data point. So I hope that you get the idea now. So I will quickly erase this. Now RBF kernel is a trick where the hyperplane acts in infinity dimensions, and it will be very difficult for me to explain that by drawing on the screen. But the main idea around that will be, if you want to classify a point at this place over here, in that case, the nearest data points that we have around that point will be considered as a weighted nearest neighbor technique. And depending upon that, we will classify that particular point. This might sound slightly overwhelming at this point of time. And trust me, if you will be asked to talk around the disadvantages of this particular algorithm, then one of the key points will be choosing the correct kernel trick is one of the most difficult thing when we are working with SVMs. So you will need some experience, some practical knowledge that how do we exactly choose one of these kernels. But more or less, this was the idea around SVM or support vector machine. In a nutshell, it tries to classify between two groups or two different classes or multiple classes by drawing a decision boundary along with a margin, keeping the margin as much as possible, where we can use some hyperparameter techniques like soft margin, hard margin, etc. in order to achieve a generalized model. But the strength of the algorithm is the kernel trick that actually helps us to convert our data set from lower dimension to higher dimension, so that we can easily classify between multiple classes by drawing a straight line or hyperplane. Now let's quickly talk about the advantages of this algorithm. Of course, it works well with high dimensions, which is really good thing. Secondly, it will be more effective when there is an understandable margin of difference between classes. And I don't think I need to explain this further. We are already familiar with this concept that why that margin is important. Kernel trick is the strength of SVM. With correct kernel function, we can solve complex problems efficiently. Of course, we need to keep this thing always in mind. It tackles the issue of overfitting with the soft margin technique that we have already discussed so far. One of the disadvantages would be that it is not recommended for a very large data set. Let's say if you are working with big data or a data set where you have millions and millions of records. In that case, I think there would be more different approaches, bagging or boosting techniques that you can try that we are yet to explore within this playlist. Secondly, the performance declines if the data has noise, or you can say if the classes are overlapping with each other. Choosing the correct kernel function is tricky, and of course we have seen how, and it is impacted by outliers to some degree. So it is not that good in terms of handling extreme outliers, but I would say still better than logistic regression to some degree. So that was it for today's lecture. I hope that you were able to gain a decent understanding on this particular algorithm. This is a super important topic even for the interviews as well, but hopefully now you will no longer hesitate to answer any kind of question related to this particular topic. So that was it for today. Thank you very much for your time.